For today's Do Now, match each equation, graph, and name the function type. Explain your choices. Pause the video, give it a try. The focus of today's lesson is mathematical models. We're going to specifically be focusing on linear and polynomial models. A mathematical model is a mathematical description, often by means of a function or equation, of a real-world phenomenon. The idea is that we have a real-world problem, we formulate a model to show that, we solve it to make mathematical conclusions, and then we interpret what it means in the real world. We use it to make predictions, and then we test and see if it makes sense. A linear function simply means that a graph of the function is a line. The slope-intercept form of the equation of a line is written y equals mx plus b, where m is the slope and b is the y-intercept. So for example, if I was given the function f of x is equal to 3x minus 2, this line would have a slope of 3 and a y-intercept of negative 2. Now remember, the slope tells us the rise over run, the rate of change. So in this case, our slope is 3 over 1, and our y-intercept is negative 2. These are useful because they allow us to get a picture of the direction that this would look as a line. Now, in table form, we see the same relationship shown, and we can see that our rate of change is up 3 for every increase of 1 in the x value, just like we see here. And we can see that our y-intercept, or where x is 0, is also negative 2. All right, so now looking at the graph, we can see very similar things. We can see here that our y-intercept is at negative 2, and we can see our slope, right? Our rise 3, run 1. Rise 3, run 1. And depending on what we're doing in our real life situation, it's useful to be able to use a variety of representations. That is our algebraic representation, our numerical representation, or our visual representation. We're going to be starting our first example by starting with a verbal representation, and we're going to attempt to create the others. So let's take a look at example 1. As dry air moves upward, it expands and cools. If the ground temperature is 20 degrees and the temperature at a height of 1 kilometer is 10 degrees, express the temperature T in degrees Celsius as a function of the height h in kilometers, assuming that a linear model is appropriate. Let's go ahead and give that a try. All right, let's start by looking at what they tell us. So they give us 2 points, right? So they tell us that when we're at a ground height, we're at the ground, so the 0 kilometers, the temperature is 20 degrees. And then they tell us that if we are at 1 kilometer, the temperature is 10 degrees. Now we can use that information to create an equation, right? So let's just use what we've learned in Algebra 1. We know that every point has an x and a y. We'll call this first point our sub 1, and we'll call the second point x sub 2 and y sub 2. So using that, we need to find 2 things to write the equation of our line, right? Because remember, the equation of the line is based on 2 things, the slope and the intercept. So let's start by finding our slope. Okay, so the slope of our line is going to be equal to the change in y over the change in x. Okay, so our y values went from 20 degrees to 10 degrees. So it changed by decreasing 10. the change in x went from 0 to 1 kilometer. So it went up 1 kilometer. So our slope is negative 10 degrees over 1 kilometer. Or just in this case, we'll say negative 10. Now, in order to get the full equation, we also need the y-intercept. Now remember, a y-intercept is achieved by looking at where x is equal to 0. Now we're lucky in this particular situation in that we're given the point at which x is 0. So we know that our y-intercept is in fact 20 degrees. So in order to write our equation, we're just going to piece that together. So we know the equation is y equals mx plus b, but in this case, we get y equals negative 10x plus 20 degrees. Now, because this particular problem actually would like us to use the variables h and t, let's pay close attention to what each of these is. So h is height. We actually chose that to be represented by x here. And our temperature is t, that's our y value. So we're simply going to replace those in our equation here. So our y is t, and our our height is our x. So our final model here, or a linear model, is going to be the temperature is equal to negative 10 degrees times the height plus 20 degrees. Now part B wants us to draw a graph. So once again, we know that our temperature is negative 10 H plus 20. So in creating this graph, we know that our y-intercept is at 20. So we'll start there. And we know that for each increase in kilometer, that we are dropping 10 degrees. So we know our next point is 1 kilometer, 10, and then the one that follows that will be 2, 0, and so on. So our line will follow this sort of path. And let's pretend that's straight. Now part C says, what is the temperature at a height of 2.5 kilometers? So once again, our formula is T is equal to negative 10 H plus 20. We want to know what is our temperature at a height of at a height of 2.5 kilometers. So we're simply going to replace the H with 2.5. So we have T is equal to negative 10 times 2.5 plus 20, which is T is equal to negative 25 plus 20. So our temperature here is negative 5 degrees. All right, now let's take a look at example 2, where we're going to create a linear empirical model, meaning we're going to make observations from a real life situation and see if we can model it. Table 1 lists the average carbon dioxide level in the atmosphere measured in parts per million at the Mauna Loa Observatory from 1980 to 2002. Use the data in Table 1 to find a model for the carbon dioxide level. So we're going to be using technology to do this. So we're going to try to use Microsoft Excel. Now you can also do this using your graphing calculator if you have it. So in order to do this, we're going to be taking the data, year and CO2 level, and we're going to be inputting it into Microsoft Excel. And it is important that when you input it, that it goes in exactly the same as what you see. So I'm going to be very careful, just kind of double checking that my values match what I see in the table. Because a mistype will create error in my final equation. All right, now once I have all the data typed in, what I'm going to do is I'm going to take these two columns, I'm going to highlight them. Once I have them highlighted, I will click Insert, Scatter Plot. I will then right-click any data point, but be sure that you're specifically on a point. I'm going to click Add Trend Line, and then right now I'm going to determine it as linear. I'm going to display the equation on the graph by clicking this box down here. Once I've done that, shrink this so we can see it. I could see an equation that is supposed to model this situation. So we're saying that our equation is 1.5-ish times x minus 2,734.6, where x represents the years and then y is going to represent the CO2 level. And you could see it changing over time. Now let's take that linear model that was created using technology by finding the best fit line for that data, and let's make a prediction. So it says this: use the linear model given by equation 2 to estimate the average level of CO2 in 1987. So what we're going to do is we're going to plug in 1987 for X, because that's our year. And then using our calculator, we have 1.5519 times 1987 minus 2,734.6. So we're going to estimate our CO2 level to be about 349 parts per million in that year. Whenever you use a model to make a prediction, always check for reasonableness. So if we go back to our data table, we can see that 1987 is about here. We're saying that it's about 349 parts per million. Now, is 349 reasonable based on what we see here? I would argue yes, right? So in 86, we're at 347.2, and in 88, we're at 351.5. So it would make sense that 349 would be reasonable. This is an example of what we call interpolation. Interpolation is the idea of making predictions of values that occur within a data set.